Okay, so as you know, though, in this class, our tests aren't cumulative, so we won't have a final. We sort of have our last test is on the day of the final. So do what you will with this exam. If you didn't do well on it, then that's okay. We have lots of input into your grade. The exams are only part of that. So there's class participation. The reading quizzes count as two exams, and we'll probably have one on Tuesday. About Thursday. Tuesday. She nodded. What do you want on what do you want on Thursday? Okay. What are a reading quiz on Thursday? We should actually be pretty much through this chapter by then, but let's go ahead and do one on Thursday. That's the chapter on what is that? Chapter 4, I guess. Sound, speech, and hearing. So we'll do a reading quiz on chapter 4 on Thursday. Then I also sent out a message to you about the project. I just want to talk about that right now, about the project. And I'm going to ask you to sort of tentatively, later in the class, I'm going to ask you to tentatively write down some ideas and turn them into me. That doesn't mean that you have to do that for your project, but just to sort of get the ideas going in your head. Now, the project, there's a rubric here that describes what it is that I want. I want to have 1,000 to 1,500 word paper. That's not that long. That's 4 or 5 double space pages. Um, but I want you to do word count, so it doesn't matter what font you use, or if you do single space, that's fine too. But I want 1,000 to 1,500 words, and it needs to be written on some topic that we've covered in the class, but not just the information that we did in class. So, for example, I don't know, what have we talked about? Well, we talked about torques in the body. So you might look at a particular set of muscles. I think in the email I said something like, what muscles do you use in water polo, for example? Or what type of injuries do you have in such and such a sport because of the forces that are involved in those muscles? Or we're going to get into the ear here. You could take that into further detail, like look at the cochlea or look at different hearing aids or assistants that you can use. Stuff that we may have mentioned in class, but that we don't go into greater depth. And so the paper is really for you to take something that you're interested in and then explore it further. I want to have at least 2 additional resources. That does not include the book, though you can use the book as well. Um, you turn it on Moodle. As we get closer to that time, I'll put a Moodle Turn It In assignment on Moodle. Turn It In assignment on Moodle, and it's worth 150 points. So this should be really, if you haven't done well in the exams, you really want to focus on this and make sure that you do well on it. All right. Follow the rubric on the requirements. When is it due? Um, do I have a due date? Late, like maybe the last class day or next to last class. Let me see. Yeah, I don't have a date on it. Hmm. Let's do May 2nd. Okay, the very last class day. So we'll just have it due on that day. All right. But when we get into April and May, I'll put a link on Moodle. So if you want to go ahead and do it now, that's fine. Let's see. Alrighty. Any questions about that? You want to be thinking about that. And at the end of class, I'll ask you to tentatively put out some ideas for that paper. So you'll just write them on a sheet of paper and just tentatively thinking about it. Not necessarily that's going to be your final idea, but to help you get those ideas going. All right. Reading quiz on Thursday. Remember, reading quiz on Thursday. Actually, let me send myself a note about that just a second. All right. We have started on waves and motion. Excuse me, waves. We talked about the 2 different kinds of waves. All waves are periodic. That means they repeat. And then we talked about 2 different kinds of waves. That is the transverse and longitudinal waves. Transverse waves, remember that the medium goes up and down, And with a longitudinal wave, the medium goes back and forth. Like the hug, remember that we did in class last time where y'all hugged one another and then you separated and then you hugged one another? Y'all remember that? Yeah, that was nice, wasn't it? Y'all like that? Anyway, transverse and longitudinal waves. You'll need to know just sort of what are those exactly, what defines them, how they're different, and the way the medium is different. Um, and then, simple harmonic motion is really the same, talking about how mediums move back and forth as they respond to some force. We talk about this in terms of a restoring force. Good way to think about this is I have a mass on a spring. And that mass on a spring moves back and forth. And in fact, it has a restoring force because if I pull a spring, it's going to try to get back to its original position. So for example, if this is what we call the equilibrium position, that's just sort of its resting position. If I pull this thing down in this direction, the mass on the spring will oscillate back and forth, back and forth. And actually, when you pull it down, there will be a restoring force that will cause the mass to go back onto its equilibrium position. Now, if we were to map this out over time, we get a graph that looks like this, that the mass goes down, and then it comes up again, it goes down and up again. So what I'm plotting here is the displacement on one axis and time on this axis. And our equilibrium position is right down the middle. Often we call this y equals 0 because that is where the equilibrium position is. That's its sort of resting position. All right, so some things that we can define about this. First of all, the equilibrium position. That is that point where it's at rest, where the restoring force is 0. Force equals 0. Or you can think of it as just sort of the at rest position. That's sort of the same thing. The amplitude is this. This is our amplitude. We use our capital A to define amplitude. We can measure it in other places, the amplitude of this wave. We can also measure the amplitude here, um, or here. Those are all our amplitudes. A period is the time for one complete oscillation. The period is the time for that wave to go one full oscillation. Oh, let's see, do I have a thing? I don't. If I imagine my mass is right here, it goes up, and then it comes back down again. That is one period. So this is t equal 1 period. The variable that we usually use for period is capital T. So we have amplitude, which is A, period is capital T, and then frequency, we'll use a lowercase script f. Frequency is the inverse of the period. It's closely related to the period. A frequency is equal to 1 over t. The frequency describes how many oscillations we get in a particular second. So whereas the period describes the amount of time per oscillation, the frequency describes the number of oscillations we get per second. So you have a wave that might have a high frequency, that means it vibrates a lot, or you in a particular amount of time, or you have a wave that has a very low frequency, that means it vibrates very little. We'll look at some graphs of those in just a moment. Now for sound waves, speed is set by the medium. Okay, and pitch is related to the frequency. So when I look at the speed of a wave, well, first of all, let me just sort of dwell on this for just a moment. A wave travels through space in a particular time. Then we had the spring all pulled out, and you pulled it back. Was that remember the big slinky? And I compressed it a little bit, and I let it go, and you could see it move back and forth across the slinky. By the way, was that a transverse wave, or was that a longitudinal wave? That type of wave, where I had the slinky all pulled out, and I compressed it, and you could see it travel back and forth along the slinky. Was that a That's a longitudinal wave. We sometimes call those compressional waves. We'll even sometimes call them pressure waves when it comes to sound anyway. So sound is a longitudinal wave. It's dependent upon the medium. Your medium will dictate how quickly that wave travels through space. So waves travel through space at different speeds dependent upon what's in that space. And we see that with sound, that sound travels through, say, metal a lot faster than it does through air, or through water a lot faster than it does through air. But we can calculate the speed of a wave by this equation, that our speed of the wave is equal to the frequency times the wavelength. Hold on just a second, let me look ahead. Okay, I'm sorry, I thought I put this in here. Let me tell you two ways that we can graph a wave. We've done this graph. This is called a history graph. And a history graph, it shows displacement versus time, but we can also show a snapshot graph. And a snapshot graph shows the wave, let's see, what is this? It's like a y versus x. So it shows the displacement in space. So if I imagine like a standing wave, you can think of this sort of as like a standing wave. So here I don't have a time on this axis, but instead I have a position. Like you get the rope and you go up and down, up and down. If you imagine that you could just freeze that thing in time so that now I have a graph that shows the y displacement as it changes going throughout space. And so in this case, our wavelength, if I look at a snapshot graph like this, a snapshot of the wave in space, in space at a particular point in time, then the wavelength is this distance. One wavelength is the distance from peak to peak on the wave. Or I can take it to be from here over to here. That's also one wavelength. Or I can take it from here over to here. That is one wavelength as well. We'll see actually that the wavelength is closely related to the frequency, but a little bit different, right? So it looks a lot like the period, but it's not the same as the period. It's a distance, not a time. That's all what I mean with the two graphs. And just sort of clarify that one more time, just to make sure, because sometimes this is confusing. This is a history graph. This shows the plot of the wave through time. So it tracks out where the wave is in time. I have the y displacement. That is how much is my medium displaced from its equilibrium position. Kind of like this mass on the spring. I pull it down to this point, and then I let it oscillate back and forth. Whereas this one is not in time. In fact, this is at one particular time. I take a snapshot of that wave and I ask, what does it look like in space? And on the x-axis, this is going through space at a particular time, kind of like when you take a rope and you go up and down, that you're taking a snapshot of the wave, and then this is still the y displacement. But that helps us to define what the wavelength of that wave is. The wavelength is not the frequency. The wavelength is not the period. It's related, but it's not the same. So I can define the speed of a wave as equal to the frequency times the wavelength. All right? Okay. So the speed of a wave is dependent upon what? When I have a wave traveling through space, the speed of a wave is dependent upon what? We just said this. What is it? Dependent. The medium, right. So waves traveling in different media will travel at different speeds. But right here, I'm saying that the speed of the wave is equal to the frequency times the wavelength. And I don't really see anything about the medium there. Is that confusing in any way to you? It seems a little confusing to me because we just said that the speed of the wave is only dependent upon the medium. And now I'm telling you that the speed of the wave is equal to the frequency times the wavelength. All right, so the speed of the wave, in fact, does not depend on either the frequency or the wavelength. It depends only on the medium. It doesn't depend on anything else. Um, so a higher frequency noise will not necessarily have a faster speed. What I'm saying in this equation mathematically is that this remains constant. So if I have a higher frequency sound in a medium, if I drive this up, then what gives? Why does my speed not increase? Just mathematically, what is going to happen to that wave if I have a higher frequency? I'll have a what? I'll have a decrease in what? My wavelength, right. So if I have a higher frequency, then I have a shorter wavelength. This sort of fits into what we think of as waves, that if I have a higher frequency, my snapshot graph will go from looking like that, or excuse me, my history graph, everything sort of squeezes together, right? Y'all understand, if I have a higher frequency, I have more peaks in a given amount of time. And so it sort of drives, the two graphs are interrelated. If I have a higher frequency, then this thing is going to collapse down in space too, so that I'll have a shorter wavelength. All right, we'll see some more of that, okay? Um, in air, sound travels at about 340 meters per second. You don't really need to know that number, but it's just there, so you can impress your friends. Um, Usually in musical instruments, the larger the instrument, the frequency of the sound is different. Any of y'all playing band or anybody? Most of y'all are athletes in high school, right? Any of you playing the band? Just me? I'm the only one that played in the band? I guess I'm the nerd in the group, right? The dork. Am I the only dork in this room? You know what I played? Guess what I played? What? The tuba. Yes, I played the tuba. The tuba is a big instrument, is it not? You ever seen a tuba? Or a sousaphone, the big thing that you wear like this. Um, it's a big instrument. And so usually in musical instruments, the bigger they are, what? The lower or the higher the pitch? The lower the pitch, right. So usually with um, musical instruments, the larger the instrument, the lower the frequency of sound. And so, for example, a tuba has a much lower frequency than a piccolo, for example. Because you've seen a piccolo, right? A piccolo is like this long. I'm not sure why they have those things in the marching band because, they don't really make much noise. But a tuba has a much bigger instrument and a much lower pitch. Likewise, with a guitar and a bass, and a guitar, it's sort of like that. Whereas a bass has a much longer neck, and it's just a bigger instrument. The strings are longer, the strings are fatter. It's just a bigger instrument. Do you know what other musical instrument I play? I play the bass guitar. Now that's cool, right? To play the bass guitar. Did I tell y'all that I used to be in a band? Back a long time ago when I was in high school, I was in a heavy metal band. I'm serious. Like we had the long, greasy hair and all that business. Huh? I don't want to say a name. That was just sort of a different part of my life, and I don't want to talk about it. But I play in our church band now, or recently anyway. Let's try some of these Quicker questions. Which of these statements is not true for a longitudinal wave? Which is not true? We're doing this one on the left. Which of these is not true? All right, so a few more seconds. I'll stop at 55, 55. Like we're missing one person, I think. 3, 8, 10, 12, 14, 17, 19. All right, stopping here. Okay, good. A is right. The medium for a longitudinal wave does not move up and down. That would be a transverse wave. It instead moves back and forth. So were there any other common answers? Okay, B and C. All waves carry energy. All waves carry energy, both longitudinal and transverse. And for a longitudinal wave, the medium does move back and forth. That's like a compressional wave. Let's try this one, the one on the right. Which of these show the wavelength of this transverse wave? This, by the way, is a history or snapshot of a wave. This is a snapshot. It shows Y position versus X position. So this is a snapshot graph. Which of these shows the wavelength of this transverse wave? All right, let's stop at 50, please. 50. Okay, so for the wavelength, excuse me, we want to start at a point on the wave, and we return back to that same point. Now, it's not here, and you might think, actually, no, it would be right here. So it would be right here. So it's B is the right answer. We can measure our wavelength in a couple of different ways, right? We can measure it like we showed before, where you're just measuring peak to peak. But notice that this is also the same distance, that I want to go through one complete oscillation. That is, when I'm going through the wave, like right here, I'm on the up slope of this section of the wave. And so I go back to the same point where I'm on the up slope of that position on the wave. That is one full oscillation, one complete oscillation, which is the wavelength of that wave. All right, the velocity of wave is 2 meters per second. Its period is 2 seconds. What is the wavelength of the wave? You have some simple math calculations like this where you have to manipulate the various velocity and frequency equations. Feel free to ask your neighbor. Many of you have the wrong answer now, so feel free to ask your neighbor what they put. Remember, our speed of a wave is equal to the frequency times the wavelength. The velocity of the wave is frequency times wavelength. Okay, good. I'm going to stop at 110, 110. 5 more seconds. I'm sort of spread out a little bit. That's okay. Okay, so let's see here. Our speed is 2 meters per second. Our frequency, well, our period is 2 seconds. That's not the frequency. Our frequency then is 1 over the period. that's equal to 1/2 second, or 1/2 inverse seconds, 1/2 seconds. So this is a half. Uh, the unit for this, we'll see this a little bit later, but you'll probably know this. What is the unit for frequency? Do y'all know? It is hertz, yeah. So we'll just use hertz. The frequency of 1 hertz is 1 oscillation per second. Whoa, whoa, whoa. That's a 1 hertz frequency. And then the wavelength, well, the wavelength is what we want to know. So to solve this, I divide both sides by a half, and I get 2 divided by a half. A half goes into 2 4 times. Right? You flip the half like this when you bring it up, and that's equal to 4. So B is the right answer. D, probably you just took half of 2, right? Is that what y'all did? Or you might have not said, you might have said that the frequency is not a half, but it's 2, in which case that would give you lambda of 1. But it's not D, it's B. Practice with that a little bit. Look back at some of the old testing quizzes and you can see some practice problems for that, because you'll probably have a question like that on a test. Okay, let's see. I don't think we looked at this, but let me just try it. This part, I don't think I said this, but sure, did we say this? We did say? I think so. All right, let's just see. The loudness of a sound is most closely affected by which of these? The period, the amplitude, the frequency, or the wavelength? Yeah, I'm not sure I said this. What is, it has several things that describe a sound. The frequency, really I just have a couple of things. The frequency and the amplitude. The frequency describes what? What does the frequency describe of a sound? The pitch, right. So did I do the high-low thing for y'all? High, low, high, low. Can y'all do that? It's like patting your head and rubbing your belly at the same time. High. Can you do it? See, you can't do it, can you? Try it later. Like it took me years of practice to be able to do it. I'll try it out. All right, and so this is pitch, frequency, and the amplitude has to do with loudness. We'll talk about this later because have you ever been to one of those rock concerts or like a concert of any kind and they got those big speakers out that are actually driving the sound waves out to you? Man, you go stand next to those speakers and you can literally see them moving back and forth. They're imparting a very large amplitude to the waves. That's what they move very back and forth. So the amplitude is affected by the amplitude is closely related to the loudness. All right, I'm going to stop at 2 minutes here. So the answer is B. If you didn't get that. B. B. The answer is B. Okay, good. Okay, so remember we talked about a mass spring. That is, I have a spring, I have a mass on it. The frequency of this mass spring system is given by this. It's given as 1 over 2 pi times the square root of k divided by m. M, of course, is just the mass. But k is something called the spring constant. This describes how stiff the spring is. It's a measure of how stiff the spring is. It actually comes about from Hooke's law. I don't think we've seen Hooke's law, but I'm going to write it here. F is equal to K times X. This is our restoring force. This is our displacement. And K is our spring constant. So if I have a spring with a very large spring constant, if I displace that spring from its equilibrium position, I get a very large force. Can you think of springs that have a very large spring constant? let's say like you ever take apart your little clicker pins, you got that little spring in there, right? A little bitty spring like this. And then you have the springs on your car, which are like, like this. Which of those has a bigger spring constant? The little spring from your clicker pin or the spring from your car? From the car, right? That one, if you apply a displacement to it, it requires a really big force. Whereas the clicker pin, you don't really need that much force. So spring constant is directly related to the stiffness of the spring. A really high spring constant means you have a really stiff spring. A low spring constant means you have a really flimsy spring. Notice that the length of the spring is not in this expression. And then that means, it doesn't matter how long the spring is or how much you extend the spring, that does not affect your frequency. However, stiffer springs give a higher frequency. Just be able to manipulate this. So if I say, what if you increase your spring constant, how does that affect your frequency? If you increase the mass that's on the spring, how does that affect your frequency? It decreases it. This increases, this decreases. If I increase this, that decreases. Let me write that. So for example, if this goes up, this goes down. If this goes up, this goes up. We'll see that come up a little bit later, the mass spring system, in regards to the body and how it works. So let's also look at a vibrating spring. That's actually more important to what we're doing, but it's very similar. Can I go down from here? Vibrating spring is like, the vocal cords in your body are like on a guitar, but they work in a very similar way because you have these two little, vocal cords in your larynx that vibrate. They have a particular length, they have a particular tension, and they can make particular sounds. So for a vibrating string, they have a very similar looking formula. It's 1 over 2L T over mu, the square root of T over mu. Here, mu is the linear mass density. It's measured in units of kilograms per meter. You don't need to know the units, but I just want to put them there because they help to illustrate what linear mass density is. Listen, we know what volume mass density is. I mean, that's usually the density that we use. But sometimes when we're dealing with long, thin things, we don't need to talk about their volume density. We can talk about their mass per unit length. And that's what we'll do with a vibrating string. If I have a high mass density, that means that, for a given length of string, it has a big mass. But if I have a low mass density, for a given length of string, it has a very small mass. It's very similar to our volume density, but instead of measuring mass per unit volume, I'm measuring mass per unit length. So our linear mass density, we also have the length of the spring, and then the tension in the string. So how does the frequency vary with these certain variables? I always like to think of the guitar. I play the guitar. Does anybody play the guitar in here? So not only am I the only dork, but I'm also the only cool person in this class. Because you have to play the guitar if you want to be cool, I think. You're such dorks. Every single one of you. All right. So how does frequency vary with the variables? Well, in a guitar, I'll try to bring it in next time, but in a guitar, if you increase the tension of the string, what happens to the pitch of the string? It goes up, right? On a piano, a similar way. If you increase the tension of the string, the frequency actually increases. So if the tension goes up, this is what happens in your vocal cords. If the tension increases, the frequency increases. That should be a cue. The frequency increases. Um, if the linear mass density, the mass of your string, goes up. Listen, if you're sort of freaked out about the whole mass density, just think of the mass of the string. If I have a more massive string, then it has a higher mass density. So you can just think of it in terms of mass. So I'll just write it as mass here, though really I'm talking about the mass density. But if the mass of our string goes up, then what happens to the pitch? Well, on a bass guitar, the big strings, are those the high pitched or the low pitched strings? That's the low pitched strings, right? So if the mass goes up, the frequency goes down. And then, what's the other one? Oh, the length. If the length goes up, the frequency also goes down. I like to think of a harp. What does a harp look like? It sort of looks. Is that a harp? That's sort of a harp. But if you know anything about a harp or about a piano too, the strings, the lower strings on a piano are longer, but I have different length strings. They're actually different mass densities too. But on this end, the strings are low pitched. On this end, I have high pitched strings. So you can see that in musical instruments and stringed instruments. If you look at their strings are different. Mostly they're different in mass density, but they're also a little bit different in length. And then you can change the tension in the strings to actually change the frequency. I'll bring my guitar next time. We can see that. We're going to see another phenomenon which will be displayed in guitars as well. Okay, so let's try these two quicker questions. The spring constant describes what of a spring? The mass, stiffness, frequency, or the wavelength? All right, let's stop at 33. 33. Look at y'all, that's awesome. So B is right. Let's go on to this next one. On a piano, the highest pitched notes come from which strings? All right, just a few more seconds. Stop at 30, please. All right, good. B is right. Uh, the shortest strings are the highest frequency. The spring constant describes the stiffness. So if I have like springs on my car, very high spring constant versus like a slinky, which has a relatively low spring constant. All right. Y'all ever seen those little cans of Coke? Like the little 8-ounce cans? You know what I'm talking about? Those are awesome. You know where they make those? Minnesota. That joke never gets old, does it? Have y'all heard that one before? No. I love that joke. I like those little Cokes, honestly. I think they're just the right size. Lots of carbs in those things, right? Yeah. Okay. My wife says that I like those one, two, three, four questions too much. Because those questions are more difficult, aren't they? Like when you give four options and you have to pick the options that are correct or incorrect. Yeah, they can be difficult. What is sound? Sound is a longitudinal wave, not a transverse. Sometimes we call it a pressure wave. Sometimes we call it a compressional wave. Any one of those is okay, but we'll call it a longitudinal wave. I said sometimes I call it a pressure wave. The medium moves back and forth, and this causes high and low pressures in the medium. Oh, let's not call them high and low. Let's call them big and small pressures. so we don't get them confused with, pitch. So it causes big and small. Sometimes I have a region of high pressure, and then I have a region of small pressure. It's like the slinky as it moved through on the ground. That sometimes the pieces came together. That's high pressure, and then sometimes the pieces went apart. That's low pressure. These regions of high pressure are called condensations, and the regions of low pressure are called rarefactions. I'm going to draw it like a transverse wave, just to sort of like, kind of like the slinky. I'll draw it like the slinky. So with the slinky, sometimes they're close together, sometimes they're far apart, close together, far apart, close together. So the condensations are this part, the rarefactions are this part. This is high pressure, this is low pressure. There's not really pressure in the slinky, but when you have sound that's traveling through space in a gas, then you do get actually high and low pressure. That's pretty cool, I think. We'll look at the ear, actually, right? And so as we hear sounds, like as you hear, the sound of my voice right now, that there are physically high and low pressures traveling through the air in this room, and those high and low pressures are impinging upon your eardrum, your tympanic membrane, inside your ear, and that's actually what's allowing you to hear the sound. This feature of pressure waves is an application of the ideal gas law. We've seen this before. I'm going to write it a little bit differently than we saw it last time. PV equals NKT, where N is not the number of moles, it's the number of molecules. Your book wrote it this way. I think we might have written it this way last time, but this is the number of molecules. And as the number of molecules increases, the pressure increases. So as K goes up, or excuse me, not K, K is a constant. As N goes up, the pressure goes up. The ideal gas law. So the number of molecules in a particular region increase. Molecules are atoms, that's N. So the pressure increases. And you can think of it as the slinky. I have more turns of the slinky in a particular place because N is bigger than the pressure is also bigger. It's sort of true for the slinky, but it's a little bit different. Um, sound can also sound can also travel through solids and liquids. While it is still a longitudinal wave, we don't call it a pressure wave in this case. Right, we still have these rarefactions and condensations, but it doesn't really change the pressure of the medium, right? Because liquids and solids are incompressible, but you can still get that energy travel through a liquid or a solid. In fact, it travels, we'll see, quite well. Let's see, I have a little video. This is sort of tangentially related, but it's very interesting. It's about slinkies. It's a Veritasium video. So let's just take a moment. We'll watch it. It's not that long, I don't think, um, about how these waves travel through space. Look, I brought a little slinky here. So you can see it's sort of hard to see, as he said, but if you if you sort of train your eye, you might be able to notice it. Shoot. Wait for it to stop shaking. We talk about in astronomy how uh, waves actually travel through space. We talk about them as like information, and so that on one side of, say, the galaxy, something might happen, but then the other side of the galaxy doesn't know about it until that information has traveled to that other side of the galaxy or the solar system or whatever you're talking about. And in a similar way, you can think of this. I mean, it's an inanimate object, so it doesn't know anything. But the bottom of the spring doesn't know that it's been released until the information has traveled along the length of the string. And he was sort of talking about how the tension changes, but you can think of it as the transfer of this information. So you want to see? How it is? All right. Y'all can try that with your friends. I know they already think that you're cool because, well, you don't play the guitar, but you didn't play the tuba either, so that sort of helps. Um, let's see. Let's look at the speed of sound. The speed of sound travels at different speeds depending on the frequency, right? The speed of the wave is dependent upon the frequency. Wait, is that right? Is it right? No, that's not right. Depending on the medium, right? The sound travels at different. Oh, never mind, it races. Don't write that far. All right, so it depends on the medium. The speed depends on the elasticity of the medium. You know how stretchy is the medium. A more elastic medium has a higher speed of sound. The elasticity of a medium describes how quickly it returns to its equilibrium position when disturbed, or when displaced, rather. A spring with a high spring constant, K, is very elastic. So given, this isn't spring, it's a spring with a high spring constant K is a very elastic material. So something that if I disturb it from its equilibrium position, it will go back to that equilibrium position very readily. Right? It has a big restoring force, if we want to think of it in those terms. So which of these do you think is the most elastic? Is a solid, a liquid, or a gas the most elastic? Given what we know about how it's related to the spring constant K, which of these is the most elastic? All right, ask your neighbor what they put, because probably they put something different from you. Go ahead and ask them what they put. See what they put and ask them why. All right, we're going to stop at 55. 55. So we're sort of spread out here. A lot of you think liquid. Listen, I know why you think it's a liquid because, well, you think, I don't know, it sort of feels stretchier, right? A liquid. But when we talk about elasticity, it means how how big is the restoring force to put it back into its equilibrium position. So, what you ever have shorts that just sort of give out, right? The elastic stops working on them because if I pull on them, they don't go back to their original position. They are no longer elastic. So that's something that has a very low elasticity because if I pull on it, it just doesn't go back. Um, and of these, the one that is the most elastic, that is if I pull on it, it goes back to its original position the most readily, is a solid. So A is the right answer here. We have to think of it in terms of sort of like on a molecular basis, that if I take a molecule of that solid and I displace it a little bit, Because it's a solid, it wants to stay in its rigid position. It will very readily go back, assuming you haven't broken it, it will very readily go back to its equilibrium position. So it's sort of like the shorts that are still good, that the elastic is still good in them. They go back to their original position. You can also think of it as having a very high spring constant, a solid. It's so high, in fact, that you can't even move the darn thing, right? So like those car springs, you ever had any of those car springs? You ever try to compress one of those things? Ever picked up a car spring? No, we had one laying around our yard when I was a kid, but you can't compress those things at all because they have such a high spring constant. So when we talk of elastic things, we're talking about things that have a very high spring constant. Let's see. Steel is one of the most elastic materials, and the result is that it has a much higher speed of sound. Now, you don't need to know these speeds of sound, the values, but I do want you to know the differences in the speeds of sound between, say, air, water, or steel. Now, water, the speed of sound in water is about 1,500 meters per second. That's about 3,400 miles per hour. For steel, it's 11,400 miles per hour. And then for air, we said this before, it's 340 meters per second, which is about 760 miles per hour. So when we talk about breaking the speed of sound, we're talking about breaking the speed of sound in air. We'll see that a little bit later, breaking the sound barrier. But it's 760 miles per hour. So notice that in terms of elasticity, these go from the lowest, which is air. If I displace an air molecule, it doesn't care. It's not going back to its original position because there's very little restoring force. It's not a very elastic medium. Water, which is a liquid, it has a slightly higher elasticity, but mostly if I displace a water molecule, again, it doesn't have much restoring force. More than it had in air, but not as much as steel, for example, which has the highest elasticity of these three. All right. So the result is that speeds that sound travels much, much, much faster. Gosh, what? A factor of, well, more than 10 times faster than it does in air. So in a gas, you can change the medium. In a gas, you can change the medium to alter the speed of sound. You can do a couple things. You can increase the, you can change the molecules. Small molecules move more quickly. You can think of them as being more agile, right? So sound travels faster. You can also increase the temperature. You increase the temperature, sound travels faster. All right. So let's try these questions. In which of these, helium or air, does sound travel the fastest? Does it travel faster in helium, or does sound travel faster in air, which is a mixture of nitrogen and oxygen mainly? What does it travel faster in? A helium gas or in just air? Which of those does sound travel faster? All right, let's stop at 43. 43. Okay, good. A is right. It travels faster in the helium atom because those little helium atoms, they're just smaller. They're more nimble. They can move around more readily. They move more readily to the wave. And so the wave will actually travel faster through it. Is this statement true or false? Sounds travel faster in a gas with higher temperatures. Okay, awesome. Stop at 23. We'll go into the next one. Look at y'all. Now let's try this last one. In which does sound travel fastest? Air, water, or wood? Okay, ask your neighbor. About 4 or 5 of you have the wrong answer right now. So ask your neighbor what they put, please. Uh, which does sound travel faster in? Air, water, or wood? Ask your neighbor what they put. All right, just a few more seconds. We'll stop at, say, 50. Stop at 50. Okay, good. C is right. Um, I know it seems like sound doesn't travel through wood very well, but it actually does because it's a solid for the same reason that it travels through steel. Solids, sound will almost always travel through solids more quickly than they do through gases or liquids. So wood is the right answer. All right. Let's see. I have another video. This is a Khan Academy video, just sort of a primer on the speed of sound and some of the things that we've been talking about. Let's see. I don't think it's very long. No, it's just a few minutes long, but I think it gives a pretty good explanation of these things. Stuff we've already talked about, but just want to reiterate these things. Okay, just a couple more things, and I'll hand back your test. Okay, we can let y'all go. Breaking the sound barrier. There's a section in your book on this, and we'll watch a video probably next time about it. But breaking the sound barrier, this was first done by Chuck Yeager in 1947. And later, this was done by a land vehicle in 1997. You might have seen videos of this or seen pictures or whatever by a land vehicle in 1997. You don't need to know the dates of these, but um, we'll look at this and how this works. This was a jet-powered car. So it was a car, but it had a jet engine on it. Did I have a picture? Oh, no, that's a jet, an actual jet. The sonic boom is very similar to the wake of a boat. The boat travels at a speed faster than the velocity of the water waves. So waves in a lake, they have a particular speed, and it doesn't matter if they have a high amplitude or a small amplitude, they're still going to travel through that water at that particular speed. Doesn't matter about their frequency or their wavelength, they'll still travel at that speed. Um, but when a boat produces waves at a rate that's faster than the waves can travel, it's like the waves sort of bunch up because you got waves traveling at a certain speed, but the boat keeps producing them at a rate faster than they can get away. So you get more and more waves that sort of add up together, and then they make a big wake like that, this big wave that comes laps up on the shore. So the waves can't get out of the way, so to speak, and they add up to produce the wake seen on the shore. See if I can draw a picture of this. So if I have this boat, it's traveling with a certain speed that is bigger than the speed of the wave. It produces these waves as they come off the back of the boat, or you can think of it as producing them here. Um, but these waves come off the back of the boat where they're disturbing the water, making it go up and down and up and down. And if it was going just a slow speed, if the boat was going a slow speed, then this wave would be able to get away. But because it's going much faster than the speed of the wave itself, then these waves will sort of bunch up. And when they get over to the shore, when I get over to the shore, these multiple waves, they just sort of bunch up all into one, and it makes for a big amplitude wave. We'll see that a little bit later, and we'll talk about that next time. Let's see, there are also a number of, we'll talk about sonic booms, and I'll actually show you a couple of videos of sonic booms next time. But let me go ahead and return your test. So I'm going to stop this, and I'll actually